I also have an emulated DOM for the Adobe PDF Reader that is very essential to do anything with JavaScript, and also have support for parsing forms inside of PDF files, which is the XFA. And two other things is you can actually deploy signatures based on Yara to detect various raw objects or JavaScript or XFA forms and other things like that. And while I was doing all this, I also added code to extract features from PDFs when parsing the PDF, so that if you want to do any machine learning, you can also do that. I think there's about 20 different features that I extract out from each PDF. And you can use this tool in a standalone way, or you can use it as a library and build your own tools on top of this. The name is based on another paper which does similar emulation for browsers back in 2009 called PhonyC. So think of Phony PDF as JS Unpack, but for PDFs. So this is a graph showing the number of exploitable vulns in code exec vulns in Adobe Reader over the last few years. You'll see a sharp rise in 2008 and 2009. So there were about 4 or 5 codex vulns till 2008, but from 9 it shot up to 30 and 60 and 40, and it's just been going up. 2014 numbers are still not out, obviously, but in the last month we have almost 4 codex vulns in Reader. So, and a lot of targeted attacks, not just exploit kits, but targeted attacks have been using PDFs as the main attack platform. It's very convenient, spear phishing attacks and everything. So it's pretty much widely prevalent. A lot of previous work has been done, like I pointed in my first slide, but mostly they're all static tools. They are tools which parse the PDFs and extract objects and do some interesting things with the objects. You could like dump the streams, extract JavaScript, or other things. Other things like that. PDF Parser is probably the most popular one. It's by Didier Stevens. PPDF is another PDF analyzing framework by Jose, and PDF X-Ray is another tool by Brandon Dixon. He's my colleague at iDefense. And there have been many talks which go into very good depths about analyzing PDF, the PDF file format, and other things. The OMG what WTF PDF is a great talk by Julia Wolf on the same subject from Virus Built-In a few years ago. Didier Stevens has some more talks at Black Hat about PDF formats and how to analyze PDFs and other things on YouTube for you to see. So it's a pretty dense topic, and I'm not going to spend much time talking about the PDF file format here, although I have a few slides that do, but I'm going to talk about analyzing PDFs and JavaScript in a dynamic way. So if you want, you can actually go back and see all of these other talks for more information on the file format itself. The design for Phony PDF, this is pretty much the design. So it consumes a PDF, and there is a parser which parses out the PDF into raw PDF objects. And there is an interpreter or an analysis engine that does something with each of these objects that have been extracted from the raw PDF. And it understands JavaScript, it understands if it's a stream objects and XFA, and it actually extracts shellcode, and even for some CVEs, it'll dump the final payload. I'll talk about each of those parts of the framework. The parser is based on Didier's PDF parser. It's actually heavily modified, and it adds a lot more features than Didier's parser. The parser essentially is a character-based state machine. So it consumes each character from the PDF file, and based on that, it creates objects and it maintains state. It's possibly the best way to parse a PDF format as dense as PDFs. And we heavily modified it. We made a lot of improvements. One of the main things is the Pythonic representation of PDF objects. So we took, every time we parse out a PDF, we get the raw object out of the PDF, and we create an equivalent object in Python, which has very nice set of features and everything, that properties and functions for you to work on them. I'll show you in the next slide how it is. The parser also takes care of a lot of the obfuscation that goes into PDFs, be it for malicious or even for regular PDFs. If it is compressed, if the objects are compressed, they are decompressed, and it understands almost a dozen different compression techniques and filters also, ASCII decode filters and CCITT filters and a whole list of filters. DDS parser actually understands a few of them, but we actually went ahead and added a whole list of filters for PDF objects. And the parser also takes care, while it's actually going through the whole state machine and parsing out the PDF, it also creates all these features for machine learning. The size of the PDF, how many JavaScript objects the PDF has, and so on and so forth. It's a pretty interesting list. And while extending the parser and actually building new parts for it, the way I did it is I had on one side the PDF specification. I used 1.7, and I used the XFS specification 2.5, and I was actually looking at the spec and coding up the parser. And all of this is, again, done in Python, so it's easily hackable. I'm not sure if you can see this, but that's a PDF in VI. It does not look very good. And to parse something like this is not easy. Every time you try to do this by hand, initially for some rapid responses, we had to analyze PDFs, and we used to do this by hand. It's not fun. I can think of one other format which actually is probably tops this. That's the rich text format. Try writing a parser for that. It's pretty awesome. So this is, again, a representation of the raw object as you see it in a PDF. So if you open a PDF in a VI, this is an example, just a snippet. So this is object ID 125. Anything after percentile is a comment. So the whole line after the percentile is a comment. For those of you who have written any code in Python or any other languages, when you see these angular brackets, these, that's the beginning of a dictionary, a key value style dictionary in Adobe. So this is the start of the dictionary, and here is the end of the dictionary. And each of these are key value pairs. So subtype is a key, and widget is a value, and so on and so forth. There are about 3 or 4 different kinds of data types that go into a raw PDF. You see here, these are both key value pairs, and check out this /key2. That's a key, and the value is a bunch of numbers inside square brackets, and that is an array. That's how it is in PDF, the raw format. And the next one is the VeriSign string. So if you see anything that's inside a regular bracket, that's a string. That's how a string is represented. And the last one is, so this piece info, the key, the value is 720. That's an indirect object reference. So it's referring to an object with an ID of 72. And after this dictionary is over, what you see next is a stream and an end stream. And the end object is actually marks the end of the whole object. And anything between these two stream and end stream is basically the raw binary stream for that particular object. It's pretty nice. So the way the PDF format quickly works is when you open a PDF, at the end of the PDF there is a cross-reference table which actually has a list of the objects that are present in the PDF and their offsets and all other stuff. the crazy thing about PDFs is, although that is required by the specification, it doesn't have to be there, and the PDF still works fine. Adobe will not complain. Actually, Reader does not complain for more than half of the crazy things you can do inside a PDF. It'll quietly and silently correct itself and rebuild the whole PDF. This is just an example of the state machine. This is a verbose log from a phony PDF. You see here that it's trying to parse an object, which is basically a dictionary, and it has all these different tokens, character-based tokens, and it's going through each of those tokens, consuming them, keeps a state, and does the whole parsing. And eventually, after doing all this, it creates a Python equivalent of the same object. So what you see here in the example, the stuff in the box, the colored box, is the raw object that's extracted from a PDF. So it's a trailer, and it has a bunch of key value pairs. The size is 22, and the root object is object ID with 23. Once the parser actually consumes this whole thing, you can actually see down below on these other 3 lines. It's converted to a Python-style object, and you can actually go ahead and do interesting things with it. So if you say PDF object.dict, it'll show you the whole key value pairs in Python style, and you can work on it and build interesting tools. It's another example with more stuff. But you can see here that you can do really interesting things just based on parsing the PDF. And once you have all this stuff, you can explore the PDF. You can see what it has. I mean, in this example here for this object, you see that the type all the way at the bottom, the type is an annotation. And you can also see that the parent and the rect, both of these, the /p and the parent, the values are indirect references to different objects. And I'll show you how all of this ties into the framework. The second big block is the analysis engine. What the analysis engine does is it consumes all the parsed objects by the parser and then starts to render the PDF. It walks each and every object, and it extracts JavaScript. It actually emulates the DOM emulation, Adobe DOM, and the XFA. This is where you can also deploy Yara signatures so that you can scan for different things that you're looking for inside of PDFs. And not just across the PDF. If the PDF has different objects, and if it has, let's say, a shellcode which is compressed, and you want to write a signature for the uncompressed shellcode, you can do it. You can express that in Yara, and it'll actually match the signatures after it decompresses the object. The JavaScript part, I think, is the most interesting thing for phony PDF. It actually extracts JavaScript. It writes all the scripts to disk for you to see and analyze. But it also creates a JavaScript context and executes all the JavaScript inside that context. This is pretty cool because now you have, it's not just dumb JavaScript execution. So if the JavaScript that you extracted is searching for, let's say, an app object or a util object or something, which is only defined inside the Adobe Reader's DOM, we actually have a full emulation for all of those objects for this to make any sense when you're using this. It has heap strip, it detects heap space to a certain extent, actually pretty good extent. And again, you can also deploy Yara signatures at this level. Interestingly, Adobe Reader uses SpiderMonkey for the default implementation of JavaScript inside Reader. And they have some patches that they have done in-house, and they've released all those patches. So in an ideal way, I should have been using SpiderMonkey. In fact, I did use SpiderMonkey for the initial implementations. But the bindings for Python were not very nicely done for SpiderMonkey, and the V8 engine had great Python bindings. So I just went ahead and switched over to V8 instead. I'll explain more about how we do heap space detection. It's really simple in the next slides. And this is a simple representation of the DOM and how the phony PDF program actually does stuff. So when you extract JavaScript, the box here, think of it as the context, and this is the JavaScript that you have extracted from the PDF. So let's say you execute the JavaScript inside here, and that particular JavaScript is looking for the app object. And if you don't have any app object or the doc object or many of the other things, things are just going to fail. It's of no use. And the way the whole reader works is all the objects that get parsed by the parser, if they have any JavaScript inside them, they can programmatically access each of the objects inside from the DOM, just like a web browser. So how we do that is, so when we start analyzing the PDF, we create a fresh JavaScript context, and we start to bootstrap stuff. In the sense, we create a fake implementation of the app object, of this object, and so many other objects. And you won't believe, but there's so many malicious PDFs which actually have some interesting checks to see if they're running inside a fake Adobe Reader. And they're very interesting because they use some corner cases that are inside SpiderMonkey. And I don't use SpiderMonkey. So then I had to go back and find all those quirks in SpiderMonkey and port them over to V8. And all of this was done in pure JavaScript. And some of them are interesting. I'll show you some of them. Like I had to implement this object for the reader DOM inside JavaScript. And in SpiderMonkey, it turns out that the prototype object has an eval property built into it. It's not the case with V8. So in the bootstrap phase, one of the things I do is I do that, and I do so many other things. And other crazy things in SpiderMonkey, like the index of function that's usually called in strings. It turns out if you call index of on an undefined object in SpiderMonkey, it returns -1. But it returns undefined in V8 and other engines. So, and many other crazy things like that. And then there's hooks. So the emulated JavaScript actually hooks a lot of interesting functions, eval obviously, and a lot of the other timeout functions like set timeout and set time interval and all those other things which are heavily abused by malicious JavaScript programs. And there's of course also the XFA DOM. So when you parse the XFA forms in a PDF, even the forms can be accessed from inside JavaScript that's embedded in the PDF. So every time I actually parse and have an XFA object, I had to somehow put information about that inside my JavaScript context. And we do that. And almost always you need some way of expressing, bridging between the Python program and the JavaScript world. And I have ways in code that actually do that. You can send stuff back and forth from Python into JavaScript and JavaScript into Python, and all sorts of other crazy stuff. This probably is the most important thing and probably the most unique thing in Phony PDF compared to other tools. And it has a full DOM emulation in the sense it has a console object that's used for logging. So from inside a JavaScript snippet, if you say console.log of a message, that message actually gets bubbled all the way up into the Python framework. And that's one of the first things that are bootstrapped when the context is created. And after that, we start creating all the Adobe objects, Adobe DOM objects that are required, the collab, full screen, thermometer, util app, and all the other stuff. And there is an object hierarchy. You can't initialize one object when it depends on another object. So that's taken care of. And I'll show you here how I did that for one of the objects. But most of the implementation have generic handlers. They just log stuff to std out or to log files. But for stuff that I'm interested in, I actually write specific handlers. For example, the spell.custom dictionary open function, which was used for that CVE, I have a custom implementation. So if JavaScript ever calls that function from inside a PDF, I would log it. And I would actually log the arguments and other things related to it. But for, let's say, other functions, so spell.xyz function, which you have no idea about, that will have its own generic handler, which will just log to a file. It also does argument introspection in the sense like it does all sorts of interesting things, like it'll check how many arguments are passed to a JavaScript function and how many should have been passed, and other things like that. Sorry. This is the example that I promised you. This is an implementation of the app object in pure JavaScript. And so it declares the app object, the app class really, and it creates the different properties for this app object. And so the app.toolbar is a property which is set to true here. The reason it is set to true here, like here, is the way I built this JavaScript is kind of, I wrote a PDF file which had some JavaScript inside, and then I executed it on a real PDF reader, and it enumerated all the JavaScript objects inside, and it actually created this in an automated way. So all of these properties are real properties. Like a malicious PDF could check that if the app.viewer version is 9.2.07, do this, otherwise do something else. So all these values are from inside of a real Adobe Reader instance. And those are the properties. There's some plugins here that are standard built into the Reader plugins, like the form plugins, the ebook plugins. And all of these are like, the way they're built are all automated. And then there's the function lists that are available inside the PDF, the app object, all of these functions, the alert, beep, and other functions. And for all these functions, there's like a generic handler, which basically the implementation is that it just logs the arguments that you pass to those functions. But for the app.alert function, I have a custom handler, which will basically which will log it in a different way. And the same thing for like the spell object, which is this guy. So there was a CVE there. So if it's spell.custom dictionary open, then it'll log saying that this is potentially a CVE 1943 exploit. So that's the DOM emulation. It's pretty cool. It's done automatically. So if you want to generate the DOM for a different version of Adobe, you just have to execute the PDF, and it'll spit out the whole DOM. The other nice thing is the XML forms architecture, the XFA. This is pretty important because a lot of exploits have begun to use this, and it's a pretty easy way to figure if you're running inside a real reader or an emulated reader. And it can be done in two ways, actor forms and XML forms architecture. So the parser, when it parses out the raw objects, it extracts even XFA objects, and it parses them, it extracts any XML inside them, and if that XML has JavaScript inside them, it'll execute the JavaScript inside the same context. So when you have two different objects, when you have a pure JavaScript object and an XFA object, and if one of them creates a variable in the context, it can be accessed from the other, which is pretty cool. And I use LXML and its Python bindings to deal with all the XML stuff, but I'm actually writing code to use the built-in E3 implementation in the mini-DOM package in Python to do the same thing so that I can get rid of one dependency from phony PDF. And the bridge again. So you can bridge between the XFA to the JavaScript land or to the Python land, and it all works nice. So every time, let's say, a new field is created in the XFA DOM, it's added to a monitored list in the sense, so let's say you create a variable inside JavaScript, which is not part of the standard DOM. And let's say you call it X, and X.property A, that is added to a list of monitored objects. And if anything changes to that object, phony PDF actually reacts to it. And it's mostly, it's actually used in detecting CVE 2010-0188. And it works pretty nice. And this is the last part of the main part of the whole thing, the render process. So once this whole parsing is done and all the JavaScript is extracted and the context is created, XFA and all that stuff, then it begins to render the document. The rendering is based on the PDF specification, and I try to stay as close to the implementation that's done inside Adobe Reader. And when I say that, I mean I did not actually sit put Adobe in a debugger and see how they're doing stuff, and I didn't do it that way. I was like, if something is broken horribly in Adobe's Reader, it's the way it's going to be in phony PDF and the other way around. And so, and the render process starts by doing all that stuff by creating the context in JavaScript and then parsing out the cross-reference table and getting the trailer object. And from the trailer object, you get the catalog object. And from the catalog object is where you have the first object that gets loaded into PDF. And from there, that object could have other dependencies, and I'll show you in an example how it's done. And then it'll start to walk all the PDF objects in a dynamic way, depending on the object it is. And the nice thing about PDFs is any of these things, the cross-reference and the trailer and the catalog, which are very essential to start running a PDF, are not really required by Reader. Even if it doesn't have all of those, Reader will still work. And it will not complain, it will just work. I'll show a PDF so it makes more sense. Here's a nicer looking PDF. So for this whole thing to make sense, I don't have much time to spend on this, but I'll show something so that it makes more sense. So this is a real PDF. I just opened it in VI, and the first line is a comment. It says it's based on PDF 1.5 spec. Does it mean anything? It doesn't. It's just there. Reader doesn't care in what version of PDF you said in the comment. This is also a comment line. It means nothing because anything after the comment line is ignored. And this is how an object is defined. This is object 48. And the length is 4078, and it says the filter is fillet decode, which means the stream which starts with this object is actually compressed in standard zlib compression. And what it's basically saying is I have to use this fillet decode option to decompress that file, and once it's decompressed, it's going to be 4078 bytes. And all this is the same object. And that's the end of the object. And then another object starts here, which is object number 40, and it has all these different key value pairs. It's a type of X object, and so on and so forth. Do the objects have to be in order? They don't. They can be any which way. There's not really standard set of rules here, and it goes on and on. And at the end of the PDF, you see that it has the cross-reference table, which is an offset again from the start of the PDF, and it finally ends here. At this point, most of the PDF parsers will stop and just relax, but a lot of the malicious PDFs have another comment here saying something, and there's more stuff here. So it has a second PDF embedded there. And what Reader does is it thinks, oh, this is the actual PDF, and it'll override any objects that were created in the previous PDFs from the objects inside of this PDF. Some more examples. I have an object with ID 157 here, and the key value pairs, these two, this is interesting. It says that the root is the key, and this is a reference to another object called object ID 155. So it basically is saying that the root object for this PDF is 155, and if you search for 155, it should be up top someplace, 156. No, there is no object with 155. That's the nice things about PDF. And this PDF works absolutely fine. One last example of more PDFs. This is actually a malicious PDF. It's CVE. It's CVE 2010-0188, which is probably the most abused CVE for PDFs that we come across. And the same thing again. It has all this object IDs and references and so on and so forth. So the way it works, so I start walking each of the objects based on, so if one object refers to another object, I go ahead to that object and I analyze that. And if that one in turn points to a different object, I do that whole walk, and And depending on the kind of object it is, there are dynamic handlers which process all that stuff. There's 6 types of handlers really based on the type of object. There's 6 basic objects in PDFs: comments, cross-reference, trailer, start of the cross-reference table, indirect objects, and malformed objects. The type of the object is based on the slash type key inside of the raw objects. This is example from, hope you can read it, but this is a code snippet from inside Phony PDF showing how it handles one object. Here it's trying to see if the type is action, and if it is action, it does a bunch of things. It checks if there's another key called /s, and which is indicative of JavaScript. And if it actually finds that it actually extracts the JavaScript and executes it inside the context. And it also increments some features and other things. There's a lot of types that are built into Phony PDF, about 35 types, I think. These are few of them. The root, catalog, action, and all these other things. So the way the code works is pretty nice. It actually, based on the type of object it's looking at, it'll check if there is an implementation inside the code to analyze that kind of object. And if there is, it'll do that. Otherwise, there is a generic handler which processes most of the objects. This is a pretty good example, CV2188. It's one of the most popular exploit even today. It's packaged with almost every exploit kit that's out there. And you still see phishing attacks and other things that use this CVE. It's a pretty complex flow to trigger this vuln, which is basically a vuln inside Adobe Reader's TIFF parsing. And so it involves the DOM, the XFA, it involves shellcode, it involves base64 encoded TIFF objects, and Phony PDF actually chews through the whole thing and spits out the shellcode, it spits out the payload, and it actually works pretty nice. And like I said, most of the CV 2010-0188 I've come across, all of them have 2 PDF files embedded together, and most of the other tools that I've seen actually fail there. Sorry, not sure at which point you lost. So this was the previous slide, and I was talking about CV 2010-0188, and you didn't miss much really, but Phony PDF actually goes through this CV, it extracts all the necessary things, and it'll tell you that this PDF was using 2010-0188. So that's one of the nice things. You can extend Phony PDF to detect any exploit that you want. You just have to hook at the right places, and Phony PDF will do most of the stuff that you want from that point on. The code is released as open source by VeriSign, my employer. They've been kind enough to release this tool. We've been using this in-house, and it works very nicely. And the nice thing is VeriSign actually agreed to release this in 3-class BSD, which is probably the most least restrictive licenses. It's not GPL. It needs PyV8 and LXML and Yara to build and use. LXML and Yara are pretty easy for using Debian or in most of the other Linux flavors, but PyV8, God help you with that, but you need that to analyze JavaScript. And in case you don't have any of these, so you can just check out the code and run stuff, and what happens is, if it doesn't find these modules, it'll selectively disable features inside Phony PDF. So if it doesn't find PyV8, it will not execute or analyze JavaScript. If it doesn't find LXML, it will not execute XFA and JavaScript. Same thing with Yara. It will not scan for all the signatures. And you can use this tool as a standalone tool just to scan PDFs and see what they're doing. Or you can build libraries on top of this. And I really hope, one of the things I asked for releasing this tool as open source was the hope that more people will contribute, because sadly, the way the tool scans stuff is reactive. you have to tell it that teach it how to detect exploits. It doesn't take a lot. It's pretty easy to do, but you have to go through the step and teach it how to detect exploits, and it'll do it for you. And with that, I have about 8 minutes for any questions.